Okay, so here's 3.1 in Accelerated Algebra 2, solving systems using tables and graphs. So we didn't cover everything yesterday, so I want to make sure I put it in the video for you. We first start off with talking about some vocabulary. All right, the three words that we need to be responsible for in this section are systems of equations, which are just two or more equations that are solved together at the same time. We'll see a couple of examples of those later. A linear system then would have to be two or more lines, since we're talking about a linear system that are solved together. And then a solution of the system is the set of numbers, like x, y, coordinate pair, that make all equations in your system true. So these are the three words or key phrases that we're going to be talking about. A system of equations, a linear system, and then the solution of a system. So let me give you an example here in box 2. So this is an example of a system of linear equations because I have two equations. I have this top equation and I have this bottom equation, and then we're solving them both at the same time. And what we're doing is we're looking for when these are true. And this section is all about graphing and using tables, so we're going to graph and use tables to solve this. So let me bring up my calculator. Okay, here's mine, and I'm going to go to the y equals button, and I want to enter in these two equations into my calculator, but you'll notice that I can only solve for y in my calculator, so I need to solve this little equation for y before we bring that in there. So if I bring this back, I'm going to have x minus 2y is equal to 4, so negative 2y is equal to negative x plus 4, so that means if I divide by negative 2 everywhere, I'm going to get this, y is equal to 1 half x and then minus 2. So I'm going to plug that one in, and let's do the same thing with this one over here. Y is going to have to be negative 3x plus 5. That was a little bit easier. So those are the two equivalent equations from my system that I can use to plug into my calculator. So I'm going to plug this one in. So I'm going to go 0.5x, and then I'm going to go minus 2. Okay, and then my next equation down, I'm going to do a negative 3x plus 5. And then hit zoom 6, so I'm staring at the same screen. So there's my first equation, there's the 1 half x minus 2, and then here is the negative 3x plus 5. And you'll see right over here, right, it looks like there's a point where they cross, where they intersect. So that means they share a point in common. So I wonder what that point is. It looks like it's 2, negative 1. I'm going to verify that using the table. So I'm going to go to table here, second table. And you'll notice that I have some x values, I'll use the screen, x values, y values, and y values. The reason there's two y values here is because I have two different lines here, because it's a system. So what I'm looking for is when the output is the same value for my single input. And if you look down, we thought the answer was 2, negative 1. If you look down here, if I move my cursor down, you can kind of see at this point, if we plug in a 2 for x, we get a negative 1 out for both y1 and y2, referring to these lines over here. So this indeed verifies that the solution to my system of linear equations here would be 2, negative 1. So I'll bring this back down. So the solution that we would look for here is the point 2, negative 1. Did I say that right? Yeah, I did right. 2, negative 1. So what does that mean? So that means when we plug in a 2 for x here, and we plug in a negative 1 for y here, we'll get a true statement there. And we plug in a 2 for that one, and we plug in a negative 1 for that one, we'll get a true statement for that one. That's what that means to be a solution. Okay, then we had an example of, we have these two pictures, and we have the Greenland shark on the left, and we have the spiny dogfish shark on the right. And the question is, when will the sharks be equal in length? So you have to get some information from the picture. So if you look down here, they give you some information here, and they give you some information here, okay? So what we're going to do is we're going to define some variables, and then use graphs and tables to make sure that we answer the question correctly. So we have to define two things here. So I'm going to say let x equal something and let y equal something. Well, I'm comparing length to years, right? It says when, length to years, and I've been given a growth rate, okay? And that says 0.75 centimeters per year. So you'll notice that this one is 0.75 centimeters per year for the Greenland shark, but this one is 1.5 centimeters per year. But this one's birth length is much larger than this one's birth length, meaning like how big the shark is when they're first born. Okay, so I'm going to say x has to be their age in years. Okay, and then y is going to have to be its length. Because after all, right, the length depends on the years, right? The years doesn't depend on the length depends on the years. If this thing is 0 years old, well, then it's not even born yet, right? But when it first comes out, it'd be 37 centimeters and then 22. So I'm going to define my variables here. I have an independent and I have a dependent variable. From here, I'm going to write a system of linear equations. So I'm going to write this, okay? For my first one, for the Greenland shark, I'm going to say y is going to be equal to 0.75 x in years plus 37, because that's how much I started with. In the dogfish one, it's going to be y is going to be equal to 1.5 centimeters per year, so x, and then plus the length that I have here is, it starts at 22. All right, so far so good. So give me a year, or give me an age, right, in years, like 1, 2, 3, or 4, and then I'll give you a length. That's what we're doing here. So we're going to take this information, we're going to plug it into our calculator. I'll move over here so we can see it. So go to y equals, clear these two out right away, and let's put in 0.75. I'll move this up to here so you can see. We'll go 0.75x and then plus 37, and then we'll move on to here and we'll go 1.5x and then plus 22. If you need to do this yourself, just pause the video and do it. So hit zoom 6, and here is what you should see. Notice that we see this little line over here. So we need to adjust the window. So, because we can't see where these meet. So let's adjust the window here. So let's go to window. Since x is representing my age in years, I don't care anything below 0. So I'll go 0, and I'm betting this is going to take at least 30 years to happen. So I'm going to go up to 40, and I'm going to go by a scale of 10. Okay? Now think about the y-axis, right? Well, the y-axis is starting at 22 for the lowest one. So definitely I'll go from 0, and then I'll probably go up to, I don't know, I'll say 100, and we'll just go by tens, and we'll see what this looks like. Okay? Now when I hit graph, oh, there we go. I'm getting a better line of that one. That makes sense. Ooh, very good. And I'm getting one over here. So there's definitely a point where they cross, and this is in 10 years, so 10, 20, so right around 20 years, because x is age in years, and then this is its length, right? So how do we figure out where this point is? All right, it's got to be around 20. So one thing that we can do is we can go to the calculate button, we can go second, calculate, and we can do an intersection. Check it out. We can calculate an intersection. So it's asking me for the first curve. So I'm going to move to the left here, just so I know where my butterfly is here. I call this the butterfly. So I'm on the blue curve. I'm push enter. Then it's asking me for the second curve. It automatically jumps to the red line. So I'll push enter again. Ask for the guess. No, just tell me what it is. Oh, look at this. 20 exactly. Look at that. 2052. If I'd known it was going to be exact, then we can also use the table, right? Let's go second table. And then when x is 20, so if I cruise all the way down to 20, right? By getting all the way down here, you can also use the table setup. I'm just showing you. You can actually just move your cursor all the way down. And using the table, we should see the output the same for the value of x is equal to 20. And look, there it is, okay? Oh, I'm still going. Oops, stop. There it is right here. When x is 20, both fish are 52 centimeters in length. All right, there it is right there. All right, so we have now confirmed from the graph and from the table that the solution to this system is after 20 years, okay, both fish will be 52 centimeters in length. Okay, another example of a system of linear equations is using a linear regression line to calculate more comprehensive data. So check this out. I have the years from 1950 to the year 2000, and we're talking about the population of New York City and LA, and this is in millions. So the population of New York in 1950 was 12.9, and LA was 4.4. So you can see that they're each kind of rising at different rates here. So the question is, at what population will the cities be equal, and then when? So somewhere in the near future, past the year 2000, they'll probably catch up to each other. So the question is when? Well, we're going to use a linear regression to do this. That means we have to go to our stat, and we need to edit our buttons here, okay? So what we're going to have to do is we're going to have to put L1 is going to be our years, L2 is going to be New York, and L3 is going to be LA. So I'm going to put that into my calculator. Pause the video so you can see in just a second. Okay, so here's what I've done. I've taken the time here now, and I have punched into my calculators a year since 1950. So I have 0 is the year 1950 over here. And then 1960 would be 10 years after it. So I'm going to move this down, maybe you can see a little bit. Okay. And then 1970 would be 20 years after. So I have 0, 10, 20, 30, 40, 50 pertaining to the years. List 2 represents New York City in millions, 12.9, 14.8, 16.2, all the way down. And then list 3, of course, represents LA. And you can see all my numbers match there for that one, okay? So make sure you have that in your calculator first. Okay, now what we're going to do is let's turn our stat plots on. So make sure your stat plots are turned on in order to do what we're going to do. So turn on and push enter. Okay. Then what we're going to do is we're going to hit zoom and then stat. Zoom and then stat, which is option 9. Okay. So you should see something that looks to the effect of this right here, and there should be 2 of them here. Wait, hold on a second. Okay, so when you hit the graph button here, you should see this right here, but you'll notice that this is only one set of data, right? This is only comparing years to one city. I wonder which city it is. Well, the reason you only see one city is because of the way your calculator has your stat set up. So if you go back to stat plot here, you'll notice that it's graphing L1 versus L2. So list 1, remember, was years. L2 was New York City. So we have to graph years versus our third list, L3, which would be LA. So what you do is you go down to your second stat plot and you want to graph L1 versus L3. So by clicking the enter button, you can then scroll down to make L2 and L3 by noticing right here on the number 3, by hitting second and then the number 3, it changes it to list 3. Because if you'll remember, if we go back to our list, okay, or if we just go back to our edit of our list, okay, L1 was years, L2 was New York, L3 was Los Angeles. So now when we go back and we hit zoom 9, we should see both sets of data there, okay, and that's what we're looking for. So now that we have these both sets of data here, let's get the regression line for each of them and plug them in and see when they're going to intersect, okay? This is kind of a process, but we can do it. So let's go to stat, and we're going to actually calculate a regression. So we're going to go option 4, and we're going to calculate, the first one will be L1 and L2, so we'll good with this, okay? So we're going to get this answer right here. I'm looking at 0.15 x plus 12.9. So I'm going to write that down and make sure I remember it. Okay, so this gives us our rate, and this gives us our starting population for New York. Now I'm going to go to stat, calculate. I'm going to do a linear regression again, option 4, except this one I'm going to change from L2 to L3. So go second, 3, that changes it to an L3 because I want my third list in there being LA. Enter, enter, enter. And I'm getting a linear regression of 0.25 plus 3.8. So I'm going to write that down, make sure I remember it. Okay, now I've written them down. I'm going to actually go back and I'm going to graph each of those on the line. So I'm going to go 0.15x plus 12.9. This is going to be my regression line for the population of New York. And then I'm going to do 0.25x and then plus 3.8. That's going to be my regression line for Los Angeles, and then I'm going to hit graph, and I should see, ooh, look at that. I have a nice regression line for that, and then I have a nice regression line for that, and it looks like eventually at some point they're going to meet each other, okay? And remember, X is in years, so this is 1960, 70, 80, 90, the year 2000, so I should go back to my window and extend my years out. Okay, so instead of 55, I'm going to maybe extend this to 85. Let's see if that will give me something. And then I'm going to hit graph and see, ooh, look at that. That's looking pretty good. And then, ooh, am I going to make it? Am I going to make it? Oh, shoot. Looks like I need to extend it both ways. Okay, so I'll go back to my window here. Okay, I should go extend this up to an X maximum. Maybe let's go 100. And then let's extend the Y maximum here. And let's go up to, I don't know, we'll go to 35. And then we'll hit graph that. Okay, this is looking a lot better here. So based on the data here, right, we've created this regression line, and then at some point it looks like they're going to meet over here. Remember, X is in years, Y is in population in millions, okay? So at some point, the population of LA is going to take over the population of New York. So when will that point be? What will the years be? What will the population be? Well, we can figure out that intersection point by going stat, or sorry, excuse me, second calculate, and we can get an intersection point, option 5. So here's first curve 1, second curve, take a guess, boom, here we go. 91 years after 1950, the population will be the same at 26.5 million people. So that's what that's trying to say right there for us, okay? 91 years after 1950, the population will be 26.5 million people for each city. So that is what we're looking for right there. Okay, 2 more quick boxes to go. Here we go. There's 2 ways we can classify a system. It can either be inconsistent or it can be consistent, all right? So we're going to start classifying these as either consistent or inconsistent. If a system is inconsistent, well, then it's pretty basic. It has no solutions whatsoever. However, if a system is consistent, it is either going to be an independent or a dependent system. So independent means it exactly has one solution, like an x and a y that intersect. Dependent means it has an infinite amount of solutions. All right, so let me give you an example of each one of these, okay? So let's say this one right here. I have negative 3x plus y equals 4. Look at this system here. These are parallel lines. There is no x value that would give us the same y value. There is no way these lines will ever cross. Therefore, this system, we could classify this as an inconsistent system. So this one is inconsistent. Okay? This one here, this is not inconsistent. It's definitely consistent because it has a single point of contact. So therefore, it is a consistent system and it's an independent. So independent consistent is how we would classify this system right here. Independent consistent. Okay, now this one, check it out. I have 2 different equations, but they represent the same line. One's on top of the other. That's an infinite amount of solutions. So this is a consistent system, but it's no longer independent. It is dependent because it has an infinite amount of solutions. That's what we call it. So that'd be a consistent dependent solution. Consistent dependent solution. There you go.